Hello, am I audible? Can you confirm? So, let's start our seventh week session. Uh,
Yes, sir.
am I audible?
Yes, sir. Yes, sir. Yes, sir.
Okay, thank you. So, let's start. So, this is week seven's interactive session. In this, in seven's video lectures, you might have learned solution solving methods for Navier-Stokes equation. Also, two new implicit methods, McCormick method and beam arming method. Also, the concept of how we can do it for compressible flows, also incompressible as well as compressible flows. So, these were the main takeaways from week seven's lectures. That is how to what to use, which techniques to use to solve for compressible flows. Also, to advanced methods of Lax-Wendorf scheme that we have studied in past weeks, uh, which are McCormick scheme and beam warming method. So moving on to questions. First question. It's a general question based on schemes. First question is explicit schemes are generally options are more computationally expensive than implicit schemes. Option B, less stable than implicit schemes for solving stiff differential equations. Option C, always unconditionally stable. Option D, not suitable for solving system of equations. You can answer the question. You can inbox the answer. Please try answering the question.
Option C, sir.
You can inbox your answer in the message box. Actually, it's not explicit and implicit schemes mainly depend on how are we suppose we are going from nth iteration to n plus 1th iteration. So here in n plus 1th iteration, uh, in what quantities or which are the points or numerical quantities that we depend to solve this n plus 1th step or n plus time step maybe or iterative step, either one. So in this n plus 1th step, which numbers or which values are we taking? If we are taking already known numbers from explicit, I mean, nth scheme, we are taking all the variables, all the numbers from nth scheme and computing n plus 1 scheme's variable, then it's called explicit scheme. Suppose if we are using a combination of n and n plus 1 steps variables, then it's called implicit scheme. So explicit schemes are generally this from with this explicit schemes can be used to solve the system directly. We may not be going into how we may not we have to go for iterations. So the one particular drawback of explicit scheme is kind of for stiff differential equation, it will be less stable or less accurate. Not stable, less accurate for using explicit schemes. Option is B. Second question. In a finite difference scheme, a higher order approximation of a derivative often leads to which of the following? First option, a simpler and less computationally expensive scheme. Option B, increased stability of the scheme. Option C, a more accurate solution but potentially less stable scheme. Option D, no change in convergence properties. So when we have a finite difference scheme and we are going for a higher order approximation, suppose we are taking uh, sorry order uh, order first order to second order, then how it will affect the scheme. Order of delta x, that is error we are taking when going from first order to second order or higher orders. What will be the changes you can notice? You can inbox your answer. Actually, when going from first order to second order or second order to third order, suppose what will happen is this is the uh, uh, order of times we are neglecting. So we will be truncating or we will be cutting off this in a Taylor series expansion. We will be eliminating or we will be disregarding the terms which will be having x cube or x square. That not x square, more than that. So we will be eliminating uh, lesser values. Suppose delta x is a
Sir,
small.
option D.
Please inbox your answers. So what will happen is that when we are truncating smaller quantities, so uh, the numerical value will go down actually. So we are only neglecting smaller and smaller values. So it will give more accurate solution actually. So option C is the answer. It will give a more accurate solution, but uh, potentially less stable scheme. So uh, when we are taking going for higher order approximation, the terms we will be including more terms in this scheme, and also it has a it can lead to a less stable scheme. It's not necessary that it will be a less stable scheme, but it can lead to less stable schemes. So answer is option C. Third question. McCormack scheme is particularly useful for which type of equation? Option 1, elliptic equation. Option B, hyperbolic equation. Option C, parabolic equation. Option D, all of the above. You can inbox your answer. Put your answers in the chat box.
Option B, sir.
Yes, you're right. It's option B, that is hyperbolic equations. McCormack scheme on also scheme is schemes we have discussing on week 7 is option B, hyperbolic equations. Again, uh, actually in week 7 it is most limited to only two schemes. So uh, in our interactive session we will be discussing a lot more deeper about these two schemes. So again, a question from McCormack scheme. The predictor step in the McCormack scheme uses a scheme that is inherently what? In McCormack scheme, the predictor step or the scheme used for the predictor step has which of the following issues or qualities? Option A, stable but not dissipative. Option B, dissipative but not stable. Option C, both stable and dissipative. Option D, neither stable nor dissipative.
Option A, sir.
It's actually option C. It is stable and dissipative. Next question. The character step in the McCormack scheme aims to which of the following? First one, A reduces dissipation introduced in predictor step. Option B, increase dissipation for stability. Option C, improve solution accuracy. Option D, all of the above.
Option C, sir.
Is option C. So actually, as well as option A can also be used. Two is wrong, but option A and B can be taken, but mainly to improve solution accuracy. Next question. A major advantage of McCormack scheme compared to that of Lax-Weintraub scheme is what? Option A, it is unconditionally stable. Option B, it is less computationally expensive. Option C, it is it has higher formal accuracy. Option D, it's better suited for steady state problems.
Option D, sir.
Actually, it's not. Uh, Option D is saying is steady state problems. So in the previous answer, you said uh, it's used for hyperbolic problems. So hyperbolic problems are not steady state problems. So, for example, our wave equations. Uh, Dou square u by dou t square is equal to alpha dou square u by dou x square. This is a second order wave equation. These kind of equations are known as hyperbolic equations, and hyperbolic equations are not steady state problems since it on the right hand side, on the left hand side, you can see the t, that is, it varies in time. So when something is varying in time, it's not steady state problem, it's a transient problem. Such problems are called transient problems. So so what is actually lax control? The McCormack scheme is a uh, improvement of lax control scheme. So McCormack scheme is a improvement of lax control scheme, and so it is improved so that it is less computationally expensive. So that is the answer is option B, less computationally expensive. Both are two-step methods, but it has been made in such a way that the second order terms are found uh, in another simpler ways, so that it the scheme becomes less computationally expensive. Next question: a major disadvantage of the McCormack scheme is what? Option A, can be overly dissipative for some problems. Option B, is difficult to implement for complex geometries. Option C, requires excessive boundary condition treatment. Option D, all of the above. So the answer is, we already said that it is dissipative, it has a dissipative property. So the disadvantage of McCormack scheme is that it can be overly dissipative for some problems. So our answer for this question is option A. It can be overly dissipative for some problems. Next question is on beam warming scheme or beam warming method. In what context might the beam warming scheme be used within a multi-grid algorithm? Options are a coarse grid solver, option B, a fine grid solver, option C, for residual smoothing, option D, not applicable in multi-grid methods. You can inbox your answers. So, uh, multi-grid, the idea of multi-grid is that when we have to solve for pressure, U as well as pressure, velocity and pressure. So velocity will be having one grid. This one particular grid will be having used to solve velocities, and other thing like uh, mm, sorry in multi-grid method, what we will use is we will be using two-step grid or multiple grids. So that first a coarse grid will be used. First First, coarse grid will be established for initial approximations. Then, finite grid will be. Then we will be refining the grids. The scheme will be refining the grids so as to get better uh, solution. So, beam farming methods are used in coarse grid solver. Option A, coarse grid solver. Question 9. In the context of numerical stability, what does numerical damping refers to? So we have already seen what is numerical stability in week 5 and week 6 lectures. So in the context of numerical stability, what does the term numerical damping, what does this term numerical damping refers to? Options are: option A, reduction of high frequency errors that may not represent the physical solution. Option B, amplification of low frequency errors that becomes dominant over time. Option C, introduction of artificial source term in the discretized equation. Option D, elimination of discretization errors altogether. You can inbox your answers. Actually, from the word meaning of the damping itself, from the word meaning of this particular word damping itself, uh, we can understand what is numerical damping. So damping means in normal uh, wave mechanics, if you think the damping is like we have a uh, wave is there. So from this kind of wave, we will have to reduce its amplitude. So we will be applying something to reduce the amplitude so that the amplitude becomes lesser and lesser as it propagates further. So such kind of thing is called a damping. So same that word meaning is applied here. So for a numerical scheme to be stable, the errors should be so numerical scheme to be stable, the errors should reduce over each iteration. So that this particular uh, time from wave mechanics is taken our damping as in like decrease of or reduction in the amplitude or the magnitude. So that is what we have taken here. So the answer is reduction of high frequency errors that may not represent physical solution. So the errors that is there in the schemes should be reduced over our iterative cycles. That is what numerical damping refers to. Answer is option A. Moving on to next question. For a stable implicit scheme, what can be said about the amplification factor compared to an explicit scheme for the same problem? Option A, it is always larger, leading to a faster growth of errors. Option B, it is always smaller, providing better numerical damping. Option C, it is always equal, signifying the same stability properties. Option D, it depends on specific problem and chosen parameters. You can try to answer the question. You can inbox your answers. So amplification factor means uh, error in the n plus 1 step by error in nth step. That is what amplification factor is. So what amplification factor is what is the uh, value of the absolute value of errors that is present in n plus 1 step with respect to that with respect to that of the errors present in the predecessor step. So this is amplification factor. So in explicit scheme, uh, uh, we know that the amplification factor or the errors grow unboundedly. So it is kind of explicit schemes are known to be uh, unstable schemes. So with respect to when comparing implicit scheme with an explicit scheme, the amplification factor is less than 1 and it is always smaller. That is, the major rule is that it should be less than or equal to 1. So it is always smaller and implicit schemes provide better numerical damping. The numerical damping can only be achieved if the amplification factor, the value of the amplification factor is less than 1. If the amplification factor is equal to 1, that the error is constant and it will remain as such. Our answer is option B. Next question uh, is on solving, discretization steps, time step, iteration steps for schemes. Question is, the Jacobi iteration method is used to solve the discretized Poisson equation. In each iteration, the value at a point is updated based on its neighbors. So the question is, what is the updated equation or updating equation for the Jacobi method? So the options are: option 1, phi nu ij is equal to phi of alt I plus 1 comma j plus phi of alt I minus 1 comma j plus phi of alt I comma j plus 1 plus phi of alt I comma j minus 1 minus f of ij. Sorry, this is uh, okay, minus f of ij. Uh, Minus f of ij star delta square by 4. Option B, phi of nu ij is equal to phi of alt ij plus omega into phi of alt I plus 1 comma j, phi of alt I minus 1 j, phi of alt I comma j plus 1 plus phi of alt I comma j minus 1 minus phi of alt I comma j, the whole divided by 4. The third option is the new phi of ij is equal to alt phi of ij minus omega into alt phi of I plus 1 comma j plus alt phi of I minus 1 comma j plus alt I j plus 1 plus alt I j minus 1 minus f of I j star f of I j into delta x square, all divided by 4. Option D, the update equation depends on specific boundary condition. That is, we can't write like this. It will be case specific. So you can try to answer the question. Our question is about stepping or iterative step of a Poisson equation. Iterative step of a discretized Poisson equation. So the question is about Poisson equation. The Poisson equation is uh, del square phi is equal to f of ij, I comma j. So here it is on two dimension. Then the equation becomes del square phi is equal to dou square u by dou x square. Sorry, dou square phi by dou x square plus dou square phi by dou y square is equal to f of ij. So when discretizing this equation, we will be getting something like this one can be with using central difference equation. Central differencing we can use phi of I minus 1
Option D, sir.
No, not the one. So while discretizing these terms in a central difference equation, it will become phi of I minus 1 j minus 2 times phi of ij plus phi of I plus 1 j by delta x square plus phi of I comma j minus 1 minus 2 times phi of ij plus phi of I j plus 1, the whole divided with delta y square. Suppose we are considering a uniform mesh. Sorry, suppose we are considering a uniform mesh. Delta x, sorry, delta y, delta x, and our I j. So this is I minus 1 comma j. This is I plus 1 j. This is I j plus 1. This is I j minus 1. So this is the end of this cross that we are taking. If we are assuming delta x is equal to delta y, that is a structured mesh, equal sides, then we can rewrite this also as delta x square. Then it will become, let me okay, then this equation will become phi of I minus 1 j, because when delta x both, sorry, here the equation is called f of ij. So this we can cross multiply. When delta x is equal to delta y, this will also become delta x square. So we can cross multiply to the right hand side, and these two terms, this term and this term, will cancel out. So the uh, remaining uh, terms will become phi of I minus 1 j plus phi of I plus 1 j plus phi of I j minus 1 plus phi of I j plus 1 is equal to, oh sorry, this one cancel out, this will go this side. Sorry, let me write one more line. The equation will become phi of I minus 1 j plus phi of I plus 1 j plus phi of j I j minus 1 plus phi of I j plus 1 minus 4 pi ij is equal to f of ij into delta x square. So if we take this negative term to this side and rearrange the equation, we will be getting an equation like this, option A. And here the question is, what is the update equation? That is, if we have this equation for first iteration, suppose n is equal to 1, first iteration. So what will be for n plus 1? So in n plus 1, if we are taking the all of the values from the old iteration, suppose solving this equation, we will be getting some answers for these 4 times. 1, 2, 3, 4, these times we are getting some answers. So if we are taking the values from taking all values from nth step to n plus 1th step, then it's called the Jacobi method. So here if you see, all the values are taken from old time step or old iteration, not time step. It's a steady state problem. Old iteration, the previous iteration. So if all the values are taken from previous iteration, it is called the Jacobi method. Suppose the left hand one, that is I minus 1 comma j and I j minus 1. These two values, that is this one and this one. If these two were phi of nu, then it would have become Gauss-Seidel method. So that's the update equation for Gauss-Seidel equation. But the question is for Jacobi method. In Jacobi method, we uses all the values from previous step or previous iterative step. So our answer is option A. Here, if we in this particular uh, option, there is no relaxation factor. If we are using any relaxation factor, that we can add extra. Relaxation is that we can uh, decide how much to take from the old values. So such methods uh, are different from Jacobi method. This is in Jacobi method, we will be taking all the old values. Next question. The McCormack scheme can be categorized as, options are: option A, finite volume scheme; option B, finite element scheme; option C, finite difference scheme; option D, spectral method. This is a simple question. Can you easily answer it? Please inbox your answer. So we have already discussed that McCormack is a improvement of lax one-drop scheme. So lax one-drop scheme we have already discussed in the last interaction section, that it's a finite difference scheme. So McCormack, if the lax one-drop scheme is an advanced form of lax one-drop scheme, then McCormack scheme is also a finite difference scheme. Our answer is option C. Next question. The McCormack scheme is particularly well suited for the problems involving which among the following? Options are option A, incompressible flows, option B, compressible flows with shocks, option C, laminar boundary layers, option D, turbulent boundary layers. You can inbox your answers. This is again a simple question. So again, this is a simple question actually. We have already discussed that McCormack scheme is uh, used for hyperbolic equations. So hyperbolic equations are mainly what wave equation kind of things. Also, in hyperbolic equations, we can also model for shock waves. And McCormack scheme is particularly useful with compressible flows with shocks. So if you can relate from these things, what kind of equations are solved by McCormack scheme, then it is easy to answer the question. Our answer is option B, compressible flows with the shocks. Actually, McCormack schemes is some earlier schemes that can detect shocks and all. Next question. How does McCormack scheme handle boundary conditions? So the question is on how the McCormack scheme, how the boundary conditions are handled by McCormack scheme. Our options are option A, it requires a special treatment at the boundaries for stability. Option B, it can use directly use of boundary values. Option C, it uses periodic boundary conditions by default. Option D, boundary conditions are not required in McCormack scheme. You can try answering the question. Options are it requires special treatment at boundaries for stability. Option B, it can directly use physical boundary values. Option C, it uses periodic boundary conditions by default. Option D, boundary conditions are not required in McCormack scheme. So in McCormack scheme, it is a second order in time as well as so both of the uh, in both side in left hand side as well as in the right hand side we will be uh, using second order uh, approximations for this Wittest equation. So when we are reaching the boundaries uh, at boundary conditions, this second order term, second order uh, establishing the boundary condition with second order schemes will be difficult. So it will be needed some special treatments at boundaries depending on the boundary conditions available. Next question, which software packages commonly use the McCormack scheme to employ CFD scheme? So in which of these software packages McCormack scheme is available? Option A, Soft ANSYS Fluent. Option B, OpenFOAM. Option C, some research code utilize McCormack scheme for specific applications. Option D, all CFD software use McCormack scheme. Again, a simple question, you can try to answer. If you have watched the videos in itself, the videos itself, the faculty is explaining that McCormack scheme is some old versions of the schemes that are being used right now. So it's a simple form. It's kind of simple but uh, understandable versions of the schemes that are being used today. So these such schemes, McCormack schemes, is not available in Fluent or open form, but these uses some uh, modified or better versions of uh, McCormack schemes or some advanced schemes other than McCormack scheme. So these schemes, so then this option A, B, and D becomes wrong. Only thing is that for some specific research purpose or specific problems, we can use McCormack scheme. Then suppose uh, we are studying some simple problems or for research purpose or something like that, we can start with McCormack scheme. So our answer is option C. Next question is on beam warming scheme. The beam warming scheme is categorized as a which of the following methods? Option A, finite difference method. Option B, finite element method. Option C, finite volume method. Option D, spectral method. Similar kind of question we saw for McCormack scheme also. So here the question is for beam warming scheme. Which kind of scheme is beam warming scheme? Is it a finite difference method? Is it a finite element or finite volume method? You can input your answers. Answer is finite difference method. Next question is, which of the following statement is about which of the following statement about finite warming scheme is false? What is the main advantage of beam warming scheme? Options are high order accuracy in time. Option B, efficient solution due to factored approach. Option C, unconditional stability. Option D, easy implementation of complex geometries. So the question is about main advantages of beam warming scheme. Options are higher order accuracy in time, efficient solution due to factored approach, unconditional stability, easy implementation for complex geometries. In beam warming scheme, we will be splitting up the uh, iteration levels or time steps. Time discretization would be much more uh, smaller than, or we will be taking intermediate steps in beam warming scheme. So our option is option B. Answer is option B, efficient solution due to factored approach. Next question. The disadvantages of beam warming scheme is option A, second order accuracy. Option B, non-iterative nature. Option C, difficulty handling boundary condition. Option D, high computational cost. Actually, high second order accuracy is not limiting. So this is an advantage, not a disadvantages. The main disadvantages is that the difficulty in handling complex boundary condition, not any boundary condition, but difficulty in handling complex boundary conditions. Next question. Which type of iteration method is sometimes used in conjunction with beam warming methods for improved convergence? Options are Jacobi iteration, Gauss-Seidel iteration, relaxation methods, all of the above. The answer is here itself. Option B, Gauss-Seidel iteration. Next question. For higher order accuracy in space, the McCormack scheme can be extended up to what? Options are lax Ventroff-like scheme. Option B, TVD, that is total variation diminishing scheme. Option C, essentially non-oscillatory scheme, ENO. Option D, spectral collocation methods. Collocation you can read as co-allocation. That is what collocation. So spectral collocation, essentially non-oscillatory, total variation diminishing, or lax butterfly scheme. Our answer is TVD, that is total variation diminishing scheme. So these schemes can be McCormack scheme can be if it is extended to a higher accuracy in space, it can be reached to something like TVD, that is total variation diminishing scheme. When compared to modern CFD methods, the McCormack scheme is considered as what? Option A fundamental building block for the understanding of numerical schemes. Option B, most efficient and accurate scheme for all CFD problems. Option C, obsolete due to the development of more advanced method. Option D, primarily used for incompressible low speed flows. So it's again a simple question on comparison of modern CFD method as well as McCormack scheme. We have discussed the difference between modern CFD method and McCormack scheme in a previous question. So what will be the answer? So if you analyze the uh, options, so in option D, primarily used for incompressible low speed flows. So uh, that we know it is not true because these schemes, all the schemes discussed in this week, that is week 7, was on compressible as well as high speed flows. Even the flows occurring, even the flows in which shocks are occurring. So from that itself, we can uh, strike off option D. Again, in option B, if you see the term, most efficient and accurate scheme for all CFD problems. This again is a negative thing. So uh, there is no scheme. There exists no scheme for all CFD problems that is most efficient and accurate. So again, this option is also uh, not true. Again, the remaining two options are a fundamental building block for understanding numerical schemes and option C, absolute due to development of more advanced method. Actually, these two can be uh, these two are true about McCormack scheme. It is somewhat absolute due to uh, uh, more advanced schemes. The absolute in a way that it is not used as such nowadays. But most apt answer from the options is option A fundamental building block for understanding numerical schemes. In the previous question, we have discussed that McCormack scheme is used for special purposes or understanding special conditions. So, in a way that McCormack scheme is a less complicated, better understandable scheme uh, from which we can learn discretization of compressible flow problems as well as problems having shock uh, problems with shock waves and all. So our answer is option A. Next question. An unconditionally stable scheme is one that. So the question is about unconditionally stable scheme. So from below options, which will suit suit more for a unconditionally stable scheme. Option A, unconditionally stable scheme is stable for any discretization step size. Option B, requires specific step size for stability. Option C, always converges to the solution. Option D, minimizes the error at each step. So the question is about unconditionally stable scheme. Options are stable for any discretization type step. Option B, requires a specific step size for stability. Option C, always converges to solution. Option D, minimize the error in each step. So, if you remember stability criteria, conditionally stable, unconditionally stable, and all, from the word itself, this unconditionality itself, we can strike out option B because it requires a specific time step. So, when there is specific when we need something specific, then it won't be unconditional. So, again, unconditionally stable means it does not it does not mean that it will converge to a solution. So again, option C is wrong because if you have remember FTCS scheme, forward in time and central in space scheme, it will be having high oscillations. So some schemes, even if sorry, this is unconditionally unstable. Uh, so even if the stability, that is stability only saying that error won't grow. The error won't be growing. It can remain same or it may reduce. It is but by saying unconditionally stable, we can't assume that it will always. The keyword is always. we can't assume that it will always converge to a solution. Again, option D minimizes the error at each step. So for minimizing the error at each step, the amplification factor should be less than 1. So that also we can't assume from unconditionally stable. Unconditionally stable means it is not the error. The only thing we can assume or we can be sure from unconditional. The word unconditional here is that it won't the error won't grow. So from the options, only A suits the solution. That the unconditional scheme is stable for any discretization time step. That itself is intuitive from the word unconditionally stable. So the answer is option A. Moving on to next questions, because this question is on well conditionedness of the system. So when solving a system of linear equations, a well-conditioned system leads to a numerical scheme with which of the following cases? Option A, high computational cost. Option B, lower round of errors. Option C, slower convergence rate. Option D, increased numerical instability. So a well-conditioned system meaning it should have a unique solution. The system should be solvable, and again change in boundary conditions should so these are the three conditions for a well-conditioned system. So from the well-conditioned systems, uh, we can't assume that it will be having uh, higher computational cost or slower convergence rate. But this one, from the word itself, we can say it is wrong, because it says increased instability. If the instability increases, then uh, the what the solving procedure as well as solvability will be decreased. So this again is wrong. So to get a unique solution, or to solve the for the system to be solvable, the round of errors should be less. From the given options, only valid option stands is option B, lower round of errors. Next question, in the context of finite difference methods, a higher order scheme is a higher order scheme typically implies what? So the question is about what do you mean from a higher order scheme? Option A, increased computational cost. Option B, faster convergence to the solution. Option C, reduce the stability of the scheme. Option D, lower accuracy compared to a lower order scheme. So what does so when we hear something like higher order scheme in finite difference method FDM, what is the meaning of that, or what does we can imply? What does the word higher order schemes we can understand? So that higher orders, and why we are going for higher order schemes? We are going for higher order schemes to what, reduce the error or increase the accuracy. So from this thing itself, this fourth option becomes cancelled. That is, it says higher order schemes have lower accuracy than a lower order scheme. So actually, why we are going for a higher order scheme? We only move for higher order schemes in order to achieve higher accuracies. Then option C is saying reduce the stability of schemes. So stability of the schemes, uh, we can't say from we can't assume that every higher order scheme will be having reduced stability. So again, that can be cancelled. Next one, faster convergence to the solution. So uh, option B, faster convergence to the solution. So this again we can't say for higher order schemes, uh, doesn't give any direct promise of faster convergence. So only thing we can say is that we know from the discretization itself is that in higher order terms, the number of terms or numbers, number of numerical values or the terms in the higher order scheme equations are high. Because when we are going for higher order schemes, there is a possibility of including higher number of terms in the discretized equation. So it will in time increase the computational cost. So our answer is option A, increase the computational cost. Next question is, the McCormack scheme is classified as. So what type of scheme is a McCormack scheme? Option A, is it a single step scheme? Option B, is it a two-step scheme? Option C, is it a three-step scheme? Option D, none of the above. So the answer is given itself here itself. So it is McCormack scheme is a two-step scheme. So why it is called a two-step scheme? Because in McCormack scheme, something called predictor character approach.
Sir,
Yes,
sir, I have a doubt in general.
yes.
Sir, the basically the McCormack scheme where we use in the industry applications.
Actually, we are not using McCormack scheme nowadays. It's actually uh, what we are studying in this course. It's all, everything is fundamental schemes that can be easily that can uh, but reflect the knowledge or what we are using today is something much advanced than these things. So McCormack scheme is a comparatively simple schemes for solving hyperbolic equations, that is even compressible flows with or without shocks. So these things, if you want to uh, model for a compressible flow, we have to add, we have to what account for the compressibility of the fluid, that is high speed flows. If the suppose we are going for high speed flows or supersonic or hypersonic flows, so in such cases the fluid becomes compressible, or it can be treated as a compressible flow. So all such cases, we can't use simple discretization schemes. So such kind of equations and flows require uh, better schemes. So McCormack scheme is a advanced version of Lax-Weintraub scheme. This Lax-Weintraub scheme is second order in space as well as time. But the thing is, it is computationally expensive, or it has more number of steps involved than McCormack scheme. So in McCormack scheme is an optimized Lax-Weintraub scheme actually. So again, McCormack scheme is second order in space and time, but uh, this is a combat simple scheme. If you ask me, it's a simple scheme, and why it is included in curriculum is because a student can understand how the compressible flows or high speed flows are being simulated. So we can't simulate compressible flows or high speed flows using the same methods or schemes that we use for incompressible Navier-Stokes equations or Euler equations for that matter. So in such places, we will be needing some advanced methods, and we have to account for the compressibility of the flow. If not, it won't. Our simulations won't reflect the uh, physical reality. So McCormack scheme is a, suppose you can take it as some basic scheme included for the student to understand how we are modeling the compressible flows or discretizing the compressible flows. This nowadays McCormack scheme as such is not used in industries. In industries, much more advanced versions or advanced techniques are used, but McCormack scheme is, we can say McCormack scheme as a basic building block. So that's why McCormack scheme becomes uh, important. It is not that, or if frankly saying, all the things we have studied, uh, uh, only a few of which are being used as such in industry nowadays. There is second order Euler is there. Also, those kind of symbol schemes are still used, but this kind of McCormack scheme is, all those things is for some particular application. and such schemes are not used as it is, but we use some advanced versions of it. But this McCormack scheme and all McCormack scheme, beam warming method, all those things, uh, we can get an understanding of how we are doing it nowadays. I hope you understood the concept. So this question is about the McCormack scheme is classified as what? So it's a two-step scheme, and schemes are two steps are prediction and correction. So we will be using first step. We will be doing it prediction. We will be modeling it as to predict things. Suppose guess thing, uh, and in later steps we will be reduce the errors or what uncertainties linked to the predictions made. So in that way, McCormack scheme is a two-step scheme. Next thing, next question. In the McCormack scheme, the predictor step uses what type of formulation? We already said that for McCormack scheme is a two-step scheme. It is a predictor corrector scheme. So this question is about what kind of formulation, what kind of uh, discretization is used in the predictor step of the McCormack scheme. Options are option 1, option A, explicit formulation, option B, implicit formulation, option C, a combination of both, option D, none of the above. You can try answering the question.
That is option C, sir. I think so.
Actually, it's little intuitive. So, so if you understand what is the difference between explicit and implicit, it will be easy. In explicit, in explicit schemes, what we do is we will be calculating unknowns from known values that we have. Suppose uh, simply saying uh, A is equal to C plus D, then we will be the only unknown will be A, C and D will be known. So such kind of formulations is explicit formulations. So here we don't have to do anything. We just do the summation of these C and D to get A. So such kind of formulation or that concept is what got explicit. So the word meaning explicitly means very thoroughly or very clearly explained, very clearly given. So such things are called explicit. Then what is implicit? Implicit, we have to calculate the unknowns from knowns and unknowns. Suppose here again day is equal to C plus D. So suppose C1 and D1. Here this C1 may be known, D1 may not be known. So here we may have to go for a system. We can only solve it by either by system of equations or iterative methods. Such a method is called implicit. So if we are going for iterative method, the we have done it. So what we will be doing, we will be guessing the values of this unknowns because uh, to A to B physically relevant, what may be the value of D1. So we will be imagining or predicting this thing when we start an iterative process. So such kind of methods are called implicit methods. So from that itself, if you say prediction and for iterative method, we have to assume it. So if you can link it together, it is a implicit formulation, not a combination of both. Or mostly, that's why it's called a predictor step. But if you ask me, yes, there is non-values there, but uh, that doesn't mean it's a combination of both. It's mostly a predictor, that is prediction step. It's an implicit formulation. Option B. This is C. Moving on to next question. The McCormack scheme is particularly useful for solving problems involving which of the following? Options are: option A, steady state flows; option B, transient flows; option C, incompressible flows; option D, none of the above. The same question we have discussed in a slightly different way previously. You can try answering the question.
Uh, Option A, sir.
Option A, yeah.
I don't know exactly. Considered or okay, sir. I don't know either A or C, but that is what I don't know which option.
Okay. So again, we have discussed that McCormack scheme is used to solve hypersonic, sorry, hyperbolic equations. So you should understand, you should at least learn some examples of these hyperbolic equations. So PD is partial differential equations are classified into three: parabolic,
Elliptic and hyperbolic.
elliptic, and hyperbolic.
Yes, sir.
So you should at least learn some examples for these type of equations, and I will write for hyperbolic since we are discussing hyperbolic. Second order wave equation or wave equations are an example for hyperbolic equations, that is dou square u by dou t square is equal to alpha uh, dou square u by dou x square. So these kind of equations are hyperbolic equations, that is it has a time term as well as space term. So when we are solving for time, then it won't be a steady state flow. When the flow or the phenomena is not changing with respect to time, it is called steady. If it is varying with respect to time, it is unsteady. So hyperbolic equation itself is representing unsteady flow phenomena. So option A becomes nullified. Option C, incompressible flows. Depends. Actually, option C is mostly depends. We can't be sure by saying itself. We can't say that incompressible flows, but because it can also be used. But for solving incompressible flows, we don't need McCormack scheme because we have done solving uh, incompressible flows. That is where uh, the equation is where density won't be changing with respect to pressure. Such kind of flows we have modeled or we have discretized with much simpler schemes. We don't be needing McCormack scheme. So again, C is wrong. So from here, since it is varying with respect to time, it is called unsteady. And another term for unsteady is transient. So our answer is option B, transient. So try to think in that way. Why it is used for, where it be applicable. Hope I am clear.
Okay, sir.
Next, next question. Compared to Lax-Weintraub scheme, the McCormack scheme offers which among the following? Option A, lower accuracy. Option B, higher accuracy. Option C, similar accuracy. Option D, none of the above. Actually, we can easily uh, uh, because in the previous questions we have discussed that McCormack scheme is an improved version of Lax-Wentworth scheme. So when something is improved version of something, uh, here in CFD it will be having higher accuracy, obviously, or at least some damping effects. So that is more stable. Either we will be going improved schemes. Why we need improved schemes? Either we need improved schemes for higher accuracy or increased stability. So these are the major concerns when coming to CFD. When why we go for improved schemes. Other thing is some special problems. So here the options, all the options are in are about accuracy. So whether it is having lower accuracy, higher accuracy, or similar accuracy. So this thing we can what strike off, since McCormack scheme is a improved version of lax on top scheme. It will be having higher but it won't be having lower accuracy. So it should either have higher accuracy, because if it was improved to get higher accuracy, then option B becomes true. If it was improved to get higher stability, then option C can be true. So here our answer is higher accuracy as well as uh, simple comparatively simple what computational procedure. So our answer is option B, higher accuracy. Next question: the McCormack scheme is more computationally expensive than which of the following schemes? Options are explicit schemes. Option B, implicit schemes. Option C, both explicit and implicit schemes. Option D, none of the above. So answer is here given here itself. Explicit schemes, because it's much simpler. We have already discussed that McCormack scheme is having two step thing: predictor, character steps. So we have also discussed that predictor and character steps is having implicit and explicit schemes. Uh, but when this one component, this predictor component, is of implicit nature, and all the implicit schemes are more computationally expensive than explicit schemes. So from that itself, we can choose the answer, that option A, explicit schemes. Moving on to next question. Boundary conditions in McCormack scheme are typically implemented using which of the following? Options are characteristics boundary condition. Option B, Dirichlet boundary condition. Option C, Neumann boundary condition. Option D, none of the above. Question is about how boundary conditions are implemented in McCormack scheme. Options are characteristic boundary conditions. Option B, Dirichlet boundary condition. Option C, Neumann boundary condition. Option D, none of the above.
Uh, option B, sir.
B, yeah. Dirichlet boundary condition. This one. So here, first thing you need to know is that McCormack scheme is second order in space, both space and time. So when we use second order discretized equation in space, the simple boundary condition that we can give is Dirichlet boundary condition. Normal boundary condition, that is when we have to discretize d by dn of something, that is Newman boundary condition. So this first order term, when we are discretizing with some second order scheme at the boundaries, will become difficult. It will reduce the accuracy, or we will have to go for some other methods. So best thing is that we will uh, model it with uh, digital boundary condition. Best possible thing if you can do is digital boundary condition. But the question itself is having some issue, like typically implemented using. It's not like that. The boundary conditions are being uh, what given or taken from physical phenomena. Suppose we have a physical or problem. So this decides what are the boundary conditions. We are not the ones deciding the boundary condition. We have to choose boundary conditions that are true to the problem or physical phenomena. So in such a way that so when you are thinking from that perspective, the question itself has some issues. But still, the point of the question is to convey that McCormack scheme is best suited with Dirichlet boundary conditions. Moving on to next question. A limitation of McCormack scheme is its what? Options are high computational cost. Option B, difficulty in handling complex geometries. Option C, low accuracy from turbulent flows. Option D, all of the above. And we already saw that the Karman scheme is having predictor corrector schemes. It's a kind of multi-step scheme. So when the scheme is multi-step scheme, the involved computational cost is high. So our answer is option A, high computational cost. That's why I have given the this very intuitive question. Moving on to next question. When solving a system of linear equations, a diagonally dominant coefficient matrix is desirable for which of the following? Option A, improved accuracy of the solution. Option B, enhanced stability of the solution method. Option C, faster convergence rate of the iterative method. Option D, reduce the requirement of the solver. So when we have a system of equation and that system of equation can be written as Ax is equal to B, where A and A, B, C, Ax, B all are matrices. This coefficient matrix, this matrix is called coefficient matrix. So this will be coefficient matrix. This will be having all the coefficients of unknown terms, that is Ax plus By. If suppose Ax plus By is equal to uh, D or something. So this A and B here, let's use C, A plus Cy, Ax plus Cy. So this A and C are the coefficient of X and Y. So these things are stored in A. Such matrix is called the coefficient matrix. And this matrix or this vector will be having x and y in a column vector, or all the unknown in a column vector or column matrix, and this will be having all the constants or whatever is in the right hand side of the equation will be having here all the values. So this matrix A, if it is diagonally dominant, that is it is having only terms in the diagonals. This what I have drawn is a tri-diagonal. It can be pentadiagonal or single diagonal, anything. So if the coefficient matrix is something like this, that is, it is having only terms in the diagonals and not in the corners. Then what will be its specialty or use? So if you see uh, here, when the matrix is diagonally dominant, then will be much more easier to solve the uh, equation than iterative method, and also it will be much more stable. That is its eigenvalues. If you know about what is the eigenvalues of the matrix, then the eigenvalue for diagonally dominant matrix are good compared to non-diagonally oriented matrices. So which in turn will increase the stability of the iterative method. So our answer is option B, enhanced stability of the iterative solution method. Next question, a scheme with high order of accuracy but poor stability might be suitable for. Options are long-term simulations. Option B, short-term simulation with high initial accuracy. Option C, solving for steady-state solutions. Option D, problems with large time constants. So here the question is about some scheme which will be having higher order accuracy, but it won't be having stability. So can we use that kind of a scheme for something useful? Options are A, long-term simulations. Option B, short-term simulation with high initial accuracy. Option C, solving for steady-state solutions. Option D, problems with large time constants.
Option A, sir.
No, wrong. So,
Okay, sir.
so first understand what is stability. Stability meaning reduction of errors. So, uh, for a stable scheme, error epsilon, suppose this is the error epsilon n plus 1 is the error in n plus 1th step, iteration step, that divided by the error in n step, that is the errors in the previous step. If you are taking the absolute value of these things, it should be less than or equal to 1. That is the stability criteria. That is, the error should not increase when we are going from one step to another. So, if the error is increasing when we are going from n step to n plus 1th step, then it is having poor instability. Poor means weak, less. So that means it is having poor stability. So in such cases, that what will happen? It is no point in running it for long time, long number of steps. So if the error is increasing step by step, then if you are running for long time, the error will be much huge. So it cannot be used for long-term simulations. From that discussion itself, we can understand. But here it's given that higher order accuracy. So the scheme is having higher order accuracy. So that even in the first step itself, the calculated value, not the solution. Uh, I mean, I am not talking about the exactness of the solution, but about the accuracy of the calculation happens in the initial steps itself will be higher. So such kind of a scheme can be used for short-term simulation with high initial accuracy. So here it is having poor stability. So the error will only increase if we are running for long. Even if you are running for short time, there will be errors, but it won't be that much compared to the scenario when we are running for long time. So it can be used for uh, what short term simulation with high initial accuracy. So our answer is option B. If you are taking option C and D, option C says solving steady state solutions. But steady state solution also needs in steady state what is that with respect to time, the variable is not uh, moving, or the thing is what the phenomena is not varying with respect to time. But there also, if we are going for iterations, there will be different steps, multiple steps will be there. So in that case also stability will be come into picture. It is not that time stepping, the iterative steps. So in steady state solution also, when we are going for iterations, stability is an issue. And also we can't say steady state solution will be short time solutions also. And option D is entirely out of the context. It is saying large time constants. So our answer is option B. Hope we can end our class for today. Thank you.
Thank you, sir. It will be really helpful for my to solve the assignments and the lecture concepts. Thank you, sir.